All right, let's begin. So we'll start off by defining what a wave is, or sometimes referred to as a progressive wave. It's a repeated disturbance that transfers energy without transferring matter. Repeated, i.e., it oscillates. It goes back and forth, back and forth, back and forth. So it completes one motion, one cycle, and then it repeats itself. By disturbance, it just means you've disturbed something. So for example, the ocean, right, before it got disturbed by whatever's causing it to get disturbed, it's flat, right? There's no like waves. There's no waves in the ocean. So this is not disturbed yet. But because of gravity, what ends up happening is the ocean gets disturbed and all of a sudden you have waves. So this is what we mean by disturbance. So any disturbance where the pattern is repeated and energy is being transferred, and we know that's the case because we could harvest energy from waves. We call this a progressive wave. But it doesn't transfer matter because, for example, an easy analogy to think of is the energy from the sun, right? We receive energy from the sun, but we don't receive any matter from the sun. We don't receive any particles, any molecules. So this is why it's called a progressive wave. So it transfers energy. It's a repeated disturbance, but it doesn't transfer any matter. So just memorize this definition in case exam question involves it. And waves can either be longitudinal or transverse, or soon we'll find out you could also have stationary waves, which is different than both of these. Okay, so let's start by talking about transverse waves, and they are oscillations. Remember, an oscillation is just a repeated disturbance. So it has oscillations perpendicular to the direction of energy transfer. So I want you to focus on one of the points on this animation below. And what you can see is that each point is oscillating up and down, up and down. So it's doing some sort of motion like this. It's going up, then it's going down, then up, then down. Whereas the entire wave is going from left to right. So the wave's energy transfer is going from left to right. So energy transfers in this direction. However, the oscillations are going up and down. So what we've noticed is that the oscillations are perpendicular, or we could say at right angles to the direction of energy transfer. So if any wave satisfies this condition, then we call it a transverse wave. So the wave is moving left to right. However, the particles or the oscillations are going up and down, and this is a transverse wave. Okay. Examples of transverse waves that you have to recognize and memorize. All electromagnetic waves. So if you remember from IGs, you have, what do you have? Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. They are all transverse waves, i.e. they all have oscillations perpendicular towards the direction of energy transfer. Ripples on the surface of water are transverse. But we're only considering the ripples because if you look at the ocean where there's waves, I'm sure you've all swam in the beach before. If not, I'll explain how it works. If you're like swimming, what you notice is the ripples take you up and then down, up and then down. So you're oscillating up and down. If you try like float on the beach, the waves are going to take you up and down, up and down. But the wave is traveling left to right. So again, the oscillations are at right angles. However, water waves are also longitudinal. There's the ripples, that's transverse, but there's also the particles below the ripples that are colliding with each other, causing the wave to move from left to right. But when we're talking about the transverse aspect, the transverse wave, we're only considering the ripples on the water. And then seismic waves, if you've done geography for IGs, they are from earthquakes, basically. When your tectonic plates have a lot of friction between them, eventually it goes beyond, from what's it called, materials, beyond its yield point. And what ends up happening is it just like kind of releases all that energy. And all of that energy in that earthquake ends up traveling to the surface, causing lots of destruction. But you need to know that it's just the S waves that are transverse. Just like we said, water waves have a transverse component, the ripples, and the longitudinal component, the actual wave. It's the same with earthquakes. There's a transverse component, and there's also a longitudinal component. The transverse waves have peaks. Peaks are areas of maximum displacement, and they have troughs, areas of minimum displacement. Good. And the equilibrium position is just like, if you didn't disturb the wave, it would be in this position. So if this was a water wave and you didn't disturb it, and all of a sudden gravity disappeared, so the waves disappear, the water will end up reaching this level. So that's what it's meant by equilibrium. Or let's say you're oscillating in a swing, okay? You're going back and forth, back and forth. Before someone pushed you on the swing, you were in the middle. So the middle is your equilibrium position. This is before you were given a disturbance. So far, so good? Now, please feel free to interrupt me. Don't be shy if something doesn't make sense. All right, let's continue. Longitudinal waves, they have oscillations parallel to the direction of energy transfer. So if we look at one of these particles, I don't know, you could focus on any particle in these animations. Maybe the red ones are easier to focus on. You're going to notice that the particle, the molecule, is vibrating or oscillating from left to right, left to right. So we've got the oscillation left to right. Whereas we have the wave also going from left to right. So if you focus on one of these lines, that's just like moving across. So the waves transfer in energy from left to right. So you could think of it as maybe a human speaking and your voice box vibrating, causing the air molecules next to it to also vibrate. And now the sound wave is going from left to right, but the particles are also vibrating left to right. So what we can say is that the oscillations, right, the vibrations are parallel. They're in the same direction as that of the energy transfer. So if a wave satisfies this condition, then all of a sudden we call it a longitudinal wave. Examples are sound waves, as we could see below. Ultrasound. Ultrasound is just like sound waves, but it has a frequency of above 20,000 hertz. Humans can't really hear ultrasound because it's beyond the range that we're able to hear. And when we're talking about ultrasound, we're usually talking about sound waves traveling through liquids or traveling through solids, because I'm not sure if you remember from IGs, sound waves travel faster if the particles or molecules are closer or more dense. That's why they travel faster in solids. Like in steel, for example, sound will travel at 6,000 meters per second, whereas in air, it's only 340 meters per second. And then finally, P waves also from earthquakes. So the earthquakes have S waves and they also have P waves. You don't need to understand the nature and too much about seismic waves, but what you do need to know, I guess, is the P waves is longitudinal and the S waves is the transverse section. Okay, longitudinal waves have something called compressions and rarefactions. So if any wave has a compression, immediately we could label it as a longitudinal wave. What are compressions? Compressions are regions of high pressure, right, due to the particles being very close together. And you could see in the animation below where the compressions are. So where the particles or molecules are really, really close, we call it a compression. Whereas if they're further apart, then it's called a rarefaction. So a rarefaction is regions of low pressure due to the particles being spread apart. Transverse waves don't have rarefactions and compressions. They have peaks and troughs. So just keep that in mind. Right, for your syllabus, there are two graphs you need to be aware of and know how to plot, and know how to deal with and extract information from. Just like in Unit 1, you had to learn about, let's say, for example, force extension graphs. You need to know that the gradient gives you the spring constant, the area underneath gives you the this. It has two other graphs that you need to know how to plot and extract some information from. The first one you've never seen before, and it's going to be really confusing when we cover it shortly. And it's called displacement distance graphs. So in the y-axis, you have displacement, and in the x-axis, you have distance. And then the second graph, you've seen it many times in IG, or even in A-level, and that's displacement time graphs. Okay, so.
Sir,
Yes, Saleh.
is it okay if you just go back to compressions and rarefactions for a second?
Mm-hmm. I've sent you all a handout on the group chat to print, by the way. So what I would advise is you print it before the sessions and answer the questions as you're going through, or as we're going through.
I have. It's just that I couldn't copy it in time.
Okay, no problem. Done?
Okay, yeah, I'm done now. Thank you.
All right, let's start with displacement distance graphs. And they show how the displacement, right, of your oscillations. So let me give you an example. Let's say I had a sound wave and I had one of the particles oscillating from left to right. Okay. The middle position, i.e., before it was disturbed, because remember, a wave is a disturbance. So before you disturb this particle, it was in the equilibrium position. As it's vibrating to the right, it's having a positive displacement, because we always say right is positive. Although that's not always the case. In your exam, they might make positive, they might make the right negative. You're just going to have to look and discover. But if they don't give you any information, then you always assume right is positive. Likewise, when it starts to vibrate to the left, it starts to have a negative displacement up until it reaches this point here, where it has maximum negative displacement. So if we look at this graph, at this section here, the particle at this section is all the way to the left. It has maximum negative displacement, whereas the particle over here, or any repeated oscillation is going to be in this section here, right? Where there's maximum positive displacement. So these graphs are really useful because it helps us understand the position of your particles as you go through the distance. Now, both the wavelength and amplitude can be acquired from this graph. The amplitude simply being the highest point, right? Or perhaps even the lowest point from the graph. This is the amplitude. So if a particle is going like this and then like this, the amplitude is like the maximum distance it is away from the equilibrium position. So that could be deduced, extracted from the graph. You just look at your graph and you go here. Just be wary, there might be some units you have to convert in the graphs given in the exam. And the second thing you could get it from it is the wavelength. And just know that the wavelength is the length of one complete cycle, one complete wave, one complete repetition, one complete oscillation. They all mean the same thing. So let's look. This wave goes up and then down. Okay. And now at this point, it's going to repeat itself. So we say from here to here is one wavelength. Because after this point, the same thing's going to happen. It's just going to repeat. It's just going to oscillate again. So the amplitude and the wavelength can be extracted from a displacement distance graph, not a displacement time graph. And those are the only two variables you could extract from a displacement distance graph. You can't extract something like the frequency, for example, of the wave, or the speed of the wave, because those are also properties of waves. But what you can is the wavelength and amplitude. Okay.
Is the graph for both types, like transverse and longitudinal?
Yeah, it's for both transverse and longitudinal. So you could have a displacement distance graph for transverse waves. For transverse waves, it's really simple. Very, very simple, because it looks just like how the wave looks like in real life. Whereas for longitudinal waves, it's a lot more complicated, because in a longitudinal wave, it's oscillating in the same direction as the wave is moving. So we're going to have to be a little bit clever when we draw these for longitudinal waves, which you're going to see shortly. But yes, they are for both transverse and longitudinal waves. Okay, so yeah, longitudinal waves are less easy to visualize from their graphs, but we're going to visualize and master it shortly. Let's consider a longitudinal wave before any disturbance. Here is the position of the particles. Naturally, they're all in the equilibrium position because you're yet to disturb it. You're not speaking, you're not pushing them, there's no car making noise. So the particles, the molecules are exactly where they are initially in the equilibrium position. Keep in mind, this is simplified. Obviously, in real life, molecules are moving because it's gas and blah, 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 but this is just for us to understand it. And it works. It's a scientific model. It works. It, allows us to predict stuff. So why not? Unlike with any area of physics, does it mean it's completely true? No, it doesn't, but it's a working model. So it's showing the initial positions. Let's say we displace this blue particle here, and it starts to vibrate. When it's vibrating and going towards the right, we would say it has a positive displacement. Whereas when it's going to the left, we're going to say it has a negative displacement. Likewise for any of these particles. So when we're talking about the displacement in a displacement distance graph, This is what we're referring to as displacement, the displacement of each individual particle. Right now, the blue one has a positive displacement, whereas the rest have a displacement of 0. Right? If you're in the equilibrium position where you started before you were disturbed, we say that the displacement is 0. Okay. Now let us consider how a compression would look like. So let's say I disturb this wave such that I have made a longitudinal wave. I know longitudinal waves have compressions and they have refractions. How would the compression look like if we were to look at the particles? Well, it would look like this, where the center of compression, which is the orange particle, as we could see, has a displacement of what? What's the displacement of the center of my compression? Who wants to tell me?
0.
0, excellent, right? How about the particle to the right of my compression? What sort of displacement does it have, Aisa?
Positive displacement.
So the red one has a positive displacement?
Yeah.
Where's its equilibrium position, the red one?
Oh, never mind. It moved to the left. Yeah, sorry. So next.
Excellent, good, because this is the equilibrium position, right, as we could see from above. And it's clearly to the left of its equilibrium position. So to the right, we have a negative displacement. How about the particle on the left, Muhammad? The blue particle, does it have a positive or negative?
Positive. It's
Excellent,
positive.
right? Because it's to the right of its initial displacement. This is going to be really, really key when we do exam questions. So yeah. So notice how the displacement of the wave at the compression, right, at the center of compression. Sometimes the exam will just call it a compression, but what it means by a compression is the center of compression. So yeah, the displacement at the compression, at the center of compression is minimum, or you could say 0. But sometimes it's not exactly 0. That's why we use the word minimum. But and it's going to be a theme actually in physics. Lots of times we're going to use the word minimum, but by minimum we mean 0. And you see what I'm talking about as we cover more and more about waves. Good. Now let's consider a rarefaction, right? A region
Sir?
of low pressure. Yes, Fizan.
So how's the blue one a positive? Isn't it to the left?
This blue one.
Oh, I thought you were talking about the other blue one. Okay, never mind.
No, I said what's the displacement of the, I guess, what color is this? Green? Green, blue? I can't even tell. Yeah, we're talking about this one. This is positive. So the particle directly to the left is positive, and the particle directly to the right is negative. The particle in the middle of the compression is 0. So now let's consider a rarefaction. Again, with a compression, we could say that the center of rarefaction, or maybe just the rarefaction, because they don't always use the word center, it has a displacement of 0. Because as you can see, the black particle is exactly in its equilibrium position. It's not being disturbed. It's not to the left of where it started, and it's not to the right. So the center of compression and the center of rarefaction have a displacement of 0. However, what's different about the particle on the right and the particle on the left? Who wants to tell me? What's different for rarefaction compared to a compression?
So is it that the particles that are closest to the center of rarefaction go away from it? So if it's to the left, it will have a negative displacement, and if it's to the right, it'll have a positive.
Beautiful, which is the opposite of it's literally the opposite of a compression. In a compression, the particle to the left has a positive displacement, whereas in a rarefaction, the particle to the left has a negative displacement. And the particle on the right of a compression has a negative displacement, whereas the particle on the right of a rarefaction has a positive displacement. And this is important, and this must be the case. Otherwise, how are you going to have a region of low pressure where the particles are far apart? For it to be far apart, the one next to it has to have a positive, and the one to its left, so the one to the right must be positive and left must be negative. Otherwise, you wouldn't get a rarefaction. So this is very, very important. And they do test you on this all the time. Okay, so let's have a go at some questions. Which of the following statements is correct for minimum displacement of the particles in a longitudinal wave? This question's for Maya when she's ready.
C.
So minimum displacement occurs at compressions and refractions. Excellent. That's what we discussed, right? In the center of compression and center of refraction, there is zero displacement. Beautiful. So this is what we take from this little section. All right, let's carry on.
Wait, sir, I have a question.
Yes.
So you can explain what minimum displacement is? I don't get it.
Minimum, it just means around zero. It means
So
zero
it just
displacement.
has to move and that's it.
It means like it's basically, it hasn't been displaced yet. It's in its equilibrium position.
Okay.
As we could see, look at the black and orange particles. They don't really have any displacement, do they? So they're at minimum displacement. That's why I said when we see the word minimum, it's easier to just start thinking about it as zero. But your syllabus uses the word minimum for reasons I'll explain later. Okay, so Asa, read this question for us and then have a go.
The diagram represents the particles in a medium before a sound wave passes through and while the sound wave is passing through. Which statement is not true?
Okay, is A true? Particle displacement is parallel.
Yes, true.
Okay, good, because it's a longitudinal wave. How about B?
It's also true.
Good. Longitudinal waves have compressions and refractions. How about C?
X. No, X is wrong, right?
Good. What should it be instead of maximum?
Minimum.
Excellent. At compression, so at X, and at refraction, so at Y, the displacement is minimum or zero.
Sir?
Yes.
So, sir, what they're saying here is that X is the point of compression, and
Yeah.
that's why it has minimum. Okay.
Yeah. They're not saying, they're showing. Right. You could see it. That's what you're going to look at and notice.
Yeah,
X is
that's what I meant.
Yeah, good. Beautiful. And
So
Y
what
is
about
obviously-
at Y?
Yeah,
Would it
Y.
be minimum or maximum?
Well, Y is the center of rarefaction, right?
Yeah.
So it'll also be minimum. And that's what we discussed literally on this slide. So for longitudinal wave, the minimum displacement occurs at both compressions and refractions. Good. So let's continue. A loudspeaker produces a sound wave in air. Diagram 1 shows air molecules before the sound wave passes, i.e. it shows the air molecules before you've disturbed, so before there's a wave traveling through it. At a particular instant, as the sound wave passes, the air molecules are displaced as shown in diagram 2. It says label a point on diagram 2 where the pressure of the air is a minimum. Muhammad, go and label for us. Is the pressure minimum here, Muhammad? Minimum meaning the molecules are far apart. I didn't ask for displacement. You've labeled me a place where the displacement is minimum, but it's asking for pressure. So you have to think about what's the definition of a compression and a refraction. So try again, Muhammad. Beautiful, excellent, very well done. So that's one place. It says label a point. It doesn't say label the point, meaning there is more than one point. So just exam score to keep.
Yeah, I didn't read the question properly at first.
Yeah, so either here or here as well. So this don't actually point in this particle or this particle, because neither of these is the an absolute minimum. Rather, the minimum is probably somewhere between these two, as you've drawn in the other side. Good, yeah. So it's asking for pressure, not displacement. Okay, now it says, at a particular instant, as the sound wave passes, the air molecules are displaced as shown in diagram 2. Sketch a graph of displacement against distance for the air particles between A and B at this instant on the axis below. I'll be really, really impressed if you're able to do that. So what I would say is, you guys, if you want, you could annotate on my screen and have your sketches, maybe use different colors. And every time I see like a wrong sketch, I'll let you know. So start sketching on this diagram. When it says sketch, it means like, you know, how's it going to look like? Is it going to look like this? Is it going to look like this? So yeah, be confident and start sketching. Where are the sketches? Go for it. Like, I'll just rub it out if it's wrong. Interesting. Who wants to join Asa? I actually really like this graph, even though it's completely wrong. It's a very good graph. Go on, Saleh, draw what you think it will look like.
Sir, I have no idea. Like my brain is blank here.
Okay, I want to give you all a hint. This is the compression. This is a refraction. This is a compression. This is a refraction, and this is a compression, right? So on this graph, there's going to be 3 compressions and 2 refractions. It's going to start with a compression. My question is, in a compression, what's the displacement? In a refraction, what's the displacement? So I guess that's
Almost zero.
my clue. And then how would it look like in between? I'll give you one more clue and I'll start it off for you. It's going to start at this point. It's going to start at a displacement of 0 and it's going to end at a displacement of 0. Okay, wow, that's a nice graph. Saleh, walk us through your graph and your thought process. Why is it that length?
Sir, I did it that length because there's oh wait, sir, I forgot there's five points. I put one less, but
No,
I
you
wanted
didn't.
to have 5.
No, you didn't. Look, there's a compression
3, 4. Oh
and
yeah,
a
I did it right.
refraction. This is a refraction, right, according to you.
Yeah.
Then this is a compression because displacement is 0. And this is a refraction. And then this is a compression. So actually, the length of your wave, the wavelength is spot on. It's fantastic. And actually, if you look at this, if you analyze this, this is 1 complete wave. This is 2 complete waves. And here it is 2 complete waves because from a compression to a compression is 1 wave. And then from a compression to a compression again is another complete wave. So this is a very, very good graph, but it's still incorrect. There's one slight inaccuracy with this graph. And I want you, my clue is, think about the displacement of our particles before and after the center of compression. Good, Isa, fantastic. And this is the correct graph because we know that in a compression, the particles on the right have a negative displacement. Let's look. Let's go back to the slide. So the particles on the right of a compression, look at the red particle, it has a negative displacement, whereas the particles on the left of a compression have a positive displacement. And that's what Asa basically did. He was showing that the particles on the right of a compression, they have negative displacement. So that is why this is a compression. This is also a compression because look, the particles on the right have a negative displacement, whereas the particles on the left have a positive displacement. This is opposite to a rarefaction, because our rarefaction here, the particles on the right have a positive displacement and the particles on the left have a negative displacement. So that is why it's this shape rather than the shape you've drew, Saleh. Does that make sense?
Yes, sir, it makes sense now.
Is everyone happy? Any questions before we move on? Shall I explain it again or shall we move on? Okay, let's move on. Dori, there'll be more practice on this. Yeah, so this is how it's going to look like. So 0 displacement for all compressions and rarefactions and 2 complete wave cycles. And it has to have the shape such that on the right is negative displacement. Good. A sound wave is moving from left to right. The graph shows displacement against position instant for the particles in the sound wave. Displacement to the right is considered positive. So this is a sort of question that tells you the direction. Anyway, it says, which of the following could show the position of these features correctly? By the way, I just want to notice, sorry, I'm backtracking, but it says the displacement to the right is positive. Even if it didn't say this, you're going to assume to the right is positive. So always assume right is positive unless otherwise specified. Okay, so what would the answer to this question be, Faizan? But I'm going to change my question, Faizan. Faizan, is X a compression or a rarefaction? Faizan, you here? Okay, Maya? Oh, he's here. Yes, Faizan?
Yes, sir. 1 second. I'm reading the question. So I'd probably say the X is compression.
Good, that's correct. X is a compression, but can you tell me why? How did you know X is a compression?
Because after it has a negative displacement, right?
Excellent, beautiful. So to the right of the particle, the displacement's negative. Good. And that's only because it says displacement to the right is considered positive. If it, for some reason, said displacement to the right is considered negative, then actually X would be a rarefaction. Good. So X is a compression, Z is a compression, Y is a rarefaction. So which is the correct answer?
So Y rarefaction, right? So
Yeah.
it's C, right?
Yes, excellent. It's C. So Y is a rarefaction and Z is a compression. X is also a compression. Okay, I feel like we've understood this topic. If not, let me know. A few more questions to practice. So the diagram represents the positions of particles before a progressive wave passes and after it passes. On the axis below, draw a corresponding graph of the displacement against position, which, by the way, position is the same as distance. So displacement position is the same as a displacement distance graph. Unlabel, it also says unlabel the wavelength. So who wants to do this question? Who's confident now that it could sketch these displacement distance graphs? I'm going to ask, go on, Maya. Do this question and walk us through your thought process.
Okay, so it starts with a compression. So it's going to start at 0 and then go negative. So there's 5 points that need to intersect because there's like 3 compressions. So there's 2 rarefactions.
Correct. So what Maya did is she noticed there's a compression, rarefaction, compression, rarefaction, compression. So she said there's 5 points of 0 displacement. Good. So let's draw 1, 2, 3, 4, 5. And then Maya also said it's going to go negative. Excellent. Let's rub yours out. Draw it again with the points I put. Good. Is job finished, or is there still one more thing we have to do, Maya?
I have to label it.
Labeled. What do you have to label?
Oh, the wavelength. So from one compression to the next.
Excellent. So you could do something like this. This is a wavelength. Or maybe from one rarefaction, this is a wavelength. This is also a wavelength if you wanted to do that, but obviously don't. Excellent. Now it says, suggest what type of progressive wave could be represented by the diagram, Muhammad.
Sir?
Yes, Saleh.
Sir, why isn't a wavelength from like one of the top points to the other top point?
That's also a wavelength. Any 2 points where it begins to repeat itself is a wavelength.
Ah, okay.
So yeah, Muhammad, what type of progressive wave is this?
Isn't it a longitudinal?
Good. And how did you know?
Because it moves back and forth.
Good. Yeah, you could clearly see that when the particles were displaced, so originally it wasn't displaced, when they were displaced to the left and right. So it's oscillating left and right, but it's also moving towards the left and right. So the oscillations are parallel to the direction of energy transfer. Therefore, it's a longitudinal wave. And also another obvious hint is there's compressions and rarefactions. You don't have compressions and rarefactions in a transverse wave. Good. So this is exactly what we drew. They were even accepting if you said a sound wave, but that's too lenient. It didn't give you any information. We can also sound wave. It could have been a water wave. Obviously, probably not because the particles are a bit too far away. Okay, so sound waves are classified as longitudinal because they, is it A, are produced by vibrations? Is it B, produce displacement along the direction of travel of the wave? C, they require medium. D, transfer energy along the direction of travel of the wave. So what do we think? Who thinks it's A? Is it longitudinal because it's produced by vibrations? The answer is no, because you could have a transverse wave produced by vibrations, i.e. your seismic waves, or your ripples on the surface of water. They are caused by vibrations, however, they are transverse. Is it B, they produce displacement along the direction of travel of the wave? Does anyone think it's B?
Yes, I think it's B.
Yeah.
Good, it's B. Excellent. It's the displacement, meaning if it's displacing in the same direction where the wave's traveling, that means it's vibrating in the same direction the wave is traveling. That means it's vibrating or oscillating in the same direction of energy transfer, because wherever the wave moves, it transfers energy. These are a bit of a trick one. And actually, when I looked at the examiner's report, a lot of students put D as the answer for some reason. D says transfer energy along the direction of travel of the wave. I think what students saw is along the direction, and they got a bit too excited and straight away tick D. Because they're thinking along the same direction, parallel has to be longitudinal. No, but what's D saying is it transfers energy on the same direction the wave is moving. This is also true for transverse waves. So if a transverse wave is moving to the right, it's transferring energy to the right. So this isn't specific to longitudinal waves. So yeah, just be slightly careful when doing these sort of questions. Okay, so another example is this slinky. Who wants to draw the displacement distance graph? Let's have Saleh. Saleh, draw the displacement distance graph for this slinky.
So does the last part of the slinky count as a rarefaction?
You tell me. Is that a compression?
No, definitely not.
Excellent. What assumption did you make, Saleh?
I don't know. I just like saw that the beginning here is this is a compression, and then here's a rarefaction, and then like just continued along the slinky.
It's not
So
really an
then I started
assumption.
at 0.
It's more of an observation. It's a factual observation. The assumption you made is right is positive. That's the assumption you made. You assume that if a particle moves to the right of the equilibrium, we consider that positive displacement. That's why a compression goes down. So yeah, how you would answer any question like this, if you haven't realized, is first label the compressions on the graph they shown. So compression, refraction, compression, refraction, compression, refraction. Then plot these on the graph, the same distance apart. So compression, refraction, compression, refraction, compression, refraction, and then consider, oh, compression, it has to go down. Oh, refraction, it has to go up. But this assumed that right is positive. If right was negative, it hasn't happened, but it's definitely in the syllabus. There's also a 1-mark question that involved left being positive and right being negative. Then it wouldn't look like this. It would look like this instead. Okay, let's continue. Very well done, Saleh. Okay, so displacement time graphs now. A lot easier. And I have a question for you all. What variables can you extract from a displacement time graph?
Velocity.
No, not velocity. It's in front of you. It's in the screen. The amplitude and the time period. Why can you get the amplitude? Well, because it has displacement on the y-axis, right? So if you know the displacement of your particles, of course you could work out the amplitude. Because what is amplitude? Just the maximum displacement. Also, you could get the time period, because in the x-axis it no longer shows distance or position. It now shows time. And if I know, like, the wave started here and then it repeated over here, this is one complete wave from here to here. So the graph will tell me the time it took to complete that one oscillation, the time it took to start here and then repeat over here. Therefore, I could deduce, or I could extract the time period from the graph. So the two things we get from this graph is the time period and the amplitude. Can you get the wavelength from this graph? Isa?
Sorry, sir, what was the question?
Can you extract the wavelength from a displacement time graph?
No.
Good, because there's no distance, there's no position in the x-axis. In a displacement distance graph, yes, you can extract the wavelength because in the x-axis, it tells you the distance. So you could work out the distance from where the wave started towards the wave ended. So therefore, you could get the wavelength. However, in a displacement time graph, it doesn't give you the distance, it gives you the time instead. So you cannot extract the wavelength. Likewise, you cannot extract the time period from a displacement distance graph because in a displacement distance graph, it doesn't tell you anything about time. So keep that in mind. But however, from both graphs, you can take the amplitude. You can take the displacement. The time period, what is the time period? The time period is defined as the time it takes the wave to complete one oscillation. So one back and forth motion, one repetition. Whereas the frequency is the number of oscillations that occur in 1 second. And if you understand what it means, what per second means, then you would understand that the difference between, or the relationship between time period and frequency is time period is 1 over frequency, or frequency is 1 over time period. So basically, what you get from this, if a question gives you the time period, you automatically know the frequency. Because you might need a frequency, because maybe you're working out speed, and speed is a wavelength times frequency, but the question doesn't give you frequency, it gives you time period instead. Don't panic. If they've given you the time period, however they gave it to you, maybe from a graph, maybe from something else, that means they've given you the frequency. Likewise, if they've given you the frequency, however that might look, they have actually given you the time period. So if you know one, you know the other, because you just do 1 over. So yeah, frequency is the number of oscillations that occur per second, meaning if you had, let's say, this much of a wave progresses in 1 second, what's the frequency? Well, the frequency is the number of oscillations per second. And how many oscillations? I have 1 oscillation plus half oscillation. So the frequency would be 1.5 hertz. Good. Equation for frequency could be written as the number of oscillations. This is the equation I made up. It's not an actual equation, but it works. Number of oscillations divided by, the time or how long it took will give you the frequency. So if I give you perhaps a more complicated example, let's say, let's look at the left. Okay, let's say this much of a wave traveled in 11 seconds. And I know it's 11 seconds because perhaps I extracted it from the graph. Like let's say here, it's 11 seconds. And then now it's asking, what is the frequency? So we're going to use the equation. Well, first of all, how much oscillations is this? Well, this is 1 oscillation. And then from here to here is half oscillation. So it's 1.5 oscillations. So I'm going to do 1.5 divided by how long did it take to complete 1.5 oscillations? It took 11 seconds. So your frequency is 1.5 over 11. So that is how you could work out the frequency. Likewise, to work out the time period is the opposite. So time period, because it's 1 over frequency, we could say time period is the time taken over the number of oscillations. And I'll let you at home figure out perhaps how you could use this, but it's very simple. Okay, so let's continue. A displacement time graph for a particular point on a transverse wave is shown. 2 times are marked, x and y. Which of the following represents the change in displacement of this point between times x and y? What I want you to do is just annotate and like tick whether you think it's A, B, or C. So everyone, when you have an answer, just tick which one you think. Is it A, B, C, or D? Where's Joanne, by the way? Always absent. Okay, we're waiting on. You all think it's D? Good. I have a question. Why isn't it B? Why is it D? The answer is because it's a transverse wave. Transverse waves oscillate at right angles towards where the wave is moving, meaning the displacement's either up or down. It's not left or right. If this was a longitudinal wave, then the answer would be B. And I guess I want you to go home and think about it. Why would the answer be B if it's a longitudinal wave? Maybe spend 5-10 minutes thinking about it and you'd understand. And that would make you a master of this topic. I think there's nothing left for you to understand on this sort of topic. Okay, so waves can be represented on graphs of displacement against distance and displacement against time, because these are two graphs you need to know. Which of the following properties can only be determined by combining information from both graphs? Isa.
So speed.
Excellent. Amplitude, you could get that from both. So it's not amplitude. Or you could get that from just one graph. So amplitude, you don't need both graphs. It's saying which can only be determined from, you need both graphs. I don't need both graphs for amplitude. I don't need both graphs for frequency. I only need the displacement time graph. I don't need both graphs for wavelength. I only need the displacement distance graph. However, speed is equal to frequency times wavelength from IG. I need the frequency, i.e. I need the displacement distance graph, and I need the wavelength, meaning I need the displacement position graph or displacement distance graph. So yeah, I need both the displacement time, and the displacement distance graph for speed. Excellent, very well done.
Sorry.
Yes.
So can you go back to the previous question? So if it was longitudinal, would it be B or C?
B. Go and tell me why.
I'm not sure why. So because isn't the displacement positive?
You're good. X is positive, but X is more positive than Y. So if I were to sketch this, let's say here is the equilibrium position. At X, let's say here's at X, it has some positive displacement. And at Y, it also has a positive displacement, but it's less positive than X. So how do I go from X to Y? Clearly, my displacement shifted to the left. Does that make sense?
Oh yeah, okay. Okay, thank you.
These little like tasks, when I give them to you, I expect like you to perhaps go home, think about it, spend like at least 10-20 minutes. And then when you don't know the answer, which I probably expect to be the case, just WhatsApp me and I'll respond if I don't have enough time. All right, okay, so waves can be represented on graphs. Oh, we did that, what am I talking about? Okay, so a sound wave travels through air.
Wait, so what's the answer to that question?
It was speed, wasn't it?
Yeah, okay.
Okay, so a sound wave travels through air. The diagram represents the displacement of air particles along the point at the instance in time. There is a compression at position V. At which position is there also a compression?
Sir, is it D?
Z. Z.
Yeah.
Good, excellent. It will be Z. What's the assumption made in this graph, Saleh? What's a bit weird?
That right is positive.
No. Right is negative. Because remember, a usual compression towards the right, it's negative displacement. For some reason, towards the right of this compression is positive, meaning it took left to be positive and it took right to be negative. And that's why I included that, because, although it's quite vague, I think the syllabus expects you to, well, it does clearly from this question. So I know it does. So you need to understand that there's an assumption involved here. This question, unlike the previous questions, involved right being negative. Okay. That's the end of lesson 1. I'm just going to end the meeting. So I have